let's talk about how we classify matter. So when we talk about matter, first we need to define what matter is. So matter is just anything that occupies space and has mass. Now, mass, it's the amount of matter that an object contains. We usually measure this in grams. So the amount of matter that, say, I contain is not ever going to change if I change locations. Like if I take myself and I go hop on a rocket right this moment to the moon, I'm still going to have the exact same amount of matter in me that I would have here on Earth. What does change, though, between, say, the Earth and the moon is weight. So weight is the effect of gravity on matter. So you might have a different weight between here and the moon, but you're still going to have the same mass. So the amount of matter in you is not going to change. So whatever number of grams you have inside you here on Earth is the same number of grams you would have inside you on the moon. So we have three main states of matter that we study: gas, liquid, and solid. So gases, these have no fixed volume, no fixed shape. Okay, so gases, they expand to fill their containers. They move around all randomly, super crazy. It's like children in a bounce house. They're going to bounce off the ground and bounce off the side, maybe bounce off the ceiling, depending on how wild they're going. Everything's super random, no fixed shape, no fixed volume. Liquids, they have random movement, but everything is close together. So stuff is still moving around. So liquids, they do have a fixed constant volume, but they don't have a fixed shape. They take the shape of their container. So in this glass, I have water. Water is a liquid. If I were to take this water and pour it into another container, the volume would still be the same, but the shape would change based on whatever the shape of the container I poured it into was. Solids, they have a fixed volume and a fixed shape. So here I have a little role-playing dice. Okay, it doesn't matter what I put it in, it's always going to have the same shape and the same volume. There is still movement inside a solid, though. There's vibration. So our atoms, we have protons and neutrons and electrons inside of them. And our protons and neutrons actually do vibrate very slightly in place. And electrons are constantly moving around. It's not anything that we can detect with our naked eye or just from holding something in our hand, but that tiny vibration still is there. Okay. So we can go between our different states of matter by heating things up or cooling things down. And you can see from these pictures, the gas is all through this container. The liquid is down there at the bottom, and then the solid is all clumped up. Okay. When we talk about solids, there's actually two types of solids to think about. There's crystalline and amorphous. So most solids that are commonly occurring are crystalline, and so they have regular repeating three-dimensional shapes. So crystalline solids is where we get really pretty crystals from that are shiny and that we can see like nice look to. Amorphous, we're not going to see that nice regularity to it. There's no internal geometric pattern. There's no shape or form to it when they are amorphous. So if I take a crystalline solid and an amorphous solid and I break them, my crystalline solids are going to cleave on very regular patterns because it is a regularly repeating surface. An amorphous solid is just going to shatter randomly. So if I drop something in the lab, my glass is amorphous, and so my glass, when it breaks, doesn't break into nice pieces, it shatters into random crazy pieces. When we go between these three main states of matter, we have specific terminology. Okay, so if I start off with a solid, if I want to go from a solid to a liquid, that's melting. If I want to go from a liquid to a solid, that's freezing. If I have a liquid and I want to go to a gas, liquid to gas is vaporizing, gas to liquid is condensing. And then there's some substances that undergo a process called sublimation. Sublimation is when we skip the liquid phase altogether and we go straight from a solid to a gas. If I have a gas that then goes straight back to a solid, it skips that liquid phase when it goes back. Gas to solid is called deposition. All right. So we have pure substances and we have mixtures. Pure substances, one substance only, definite composition, definite property. So elements are pure substances and compounds are pure substances. So if I have, let's see here. Let me grab something here. Okay, I have these really cool things called element dice. So right here, this is pure copper. So this is a pure substance. I can't chemically separate this into simpler substances. This is pure copper right here. Okay, put that back in its place. Compounds, we can separate them chemically into simpler substances. So if this is deionized water with nothing else dissolved in it, this would be a compound. All right, then we have mixtures where we put together two or more substances with variable composition. The properties are going to depend on what we have mixed together. So we have homogeneous and heterogeneous. So homogeneous, everything is uniform. With my naked eye, I cannot tell the difference between the components inside of that particular mixture. So when I make my coffee in the morning, I can't tell in my coffee cup the caffeine molecule from whatever flavor molecule, from the water molecules, from any creamer or sweetener that's put in there. It's all uniform. So that would be homogeneous. Heterogeneous is not uniform. We can see differences. So if you've ever tried to mix oil and water, they separate into distinct layers, or if you shake them up, you can still see all the little particles in there, okay? So oil and water would be heterogeneous because we can distinctly tell the difference between the components in that mixture. All right, and so here's some pictures. So there's an element that actually looks like copper as well. And then compound that they're picturing there would be sugar cubes, so that's pure sugar. And then there's some tea. So when you look at that cup of tea, you can't see all those different things, but on the particulate level, okay, when we visualize that on the particulate level, we can start to think about, oh, there's water molecules, there's caffeine molecules, there's probably sugar molecules. In fact, if you look at this and this, or actually that one and yeah, if you look at those, they, look very similar, so it's probably sugar, or this one from that angle. So homogeneous, all uniform. Heterogeneous, so here's that oil and the water, and then on the particulate level, you can see two completely different components there. All right, and then when I have my mixtures, depending on how much is in there, we might be able to see something that is deeper colored. So bromine is this orangish brownish color. So if I have pure bromine, it's going to be a nice deep color like that. Pure water, colorless. But if I dissolve some bromine in water, now I start to get that colored solution. I can't with my naked eye tell the bromine apart from the water. On the particulate level, I can visualize it. Here's water, here's water, here's water, here's bromine, here's bromine. Okay, so this would be a homogeneous mixture. Okay, because we can't tell it apart with our naked eye. So, but then if I add more bromine to it, then the color deepens because now I've made a more concentrated mixture there. Okay. Again, elements, we cannot separate them chemically into simpler substances. The only way I can screw with elements is if I have access to a particle accelerator, which I do not have access to a particle accelerator. Compounds, again, we can chemically separate them into simpler substances. Okay. So when I start to think about all of my different classifications here, matter, I have mixtures, pure substances. Mixtures fall into two categories. I can physically separate mixtures into pure substances. And then when I think about my pure substances, I have compounds and elements. All right, and then from there, compounds can be separated chemically into elements. So let's think about if we take something like aluminum. Okay, aluminum by itself, it's a metal. I cannot decompose it to simpler substances with chemical reactions. Now, there's oxides of aluminum that occur naturally. So various different gemstones are actually oxides of aluminum. Rubies and sapphires, aluminum oxides. I can alloy aluminum with various different other elements to make mixtures that can be used in various different fashions. And then aluminum ore. Okay, if I want pure aluminum, I would take something like bauxite, aluminum ore, and I would use some sort of technique to separate the components of bauxite and then isolate my metallic aluminum. All right, so we have all those different classifications. Let's just think about mixtures for a moment and think about homogeneous versus heterogeneous mixtures. Okay, so the ocean, what do you think that would be? Well, if you think about it, it could probably be based on how far away you are. Like if I'm looking at it from a distance, I've probably classify it as homogeneous. But if I'm up closer to the ocean, I can usually start to see some of the individual stuff in there because usually there's sand floating around and there's kelp floating around. So let's classify this a little bit further. Let's just say we just have an isolated sample of water. So let's say it's just the salt water. Okay. So we just scoop up a sample of just the salt water. Most likely, it would be homogeneous. Okay. If I were to get it right at the shore where a lot of sand was mixing around in it, then it could be heterogeneous. Okay. Milk. Okay. Do you see different pieces separating in milk? Not usually so, we would say. Okay, butter. Butter looks pretty uniform. What about pulp-free orange juice? Without the pulp, it should be homogeneous. And then salad dressing usually has different components in it, so this would be heterogeneous. Okay, so again, with our ocean, if it's just the pure salt water, homogeneous. If it has other stuff mixed around in it, it could be heterogeneous, depending on where you pull your sample from. Okay. All right, so that's a little bit about classifying matter.